It is time. We are starting. Proofs. Now, I need you guys to understand a few things about these. First off, trig proofs are almost nothing like geometry proofs. Well, the thing with trig proofs is they're not math problems. They're puzzles. You know, like what the problems we just got done doing. Here's an angle of elevation from a plane. Find the distance the plane is to the airport. That's a math problem, right? Like there's an answer to that. Proofs are not that. There's a totally different idea. You're going to be given the problem. You're also going to be given the answer. Your job, connect the dots. How does this become this? Like that's really all it is. So for those of you that I've been griping at lately of, hey, you need to make sure you show your work on some of these assignments. The only thing to do in the next few assignments is to show your work. Like if you don't, there's no answer to these. Like there's no bottom line, this is the answer. It's purely, you got to connect the dots. Now, Braxton, give me directions to get to Birchwood Mall. From here, how do I get to the mall in Port Huron?
Take School Road.
Take School
Drive.
School Drive.
Yale Road all the way to.
Turn right on.
No, this is Braxton.
Yale Road all the way to the water and then.
Take Yale Road to the water.
Take a right.
Hang a right. Okay. Madeline, will you give me directions to the mall, please?
Go to Yale Road.
Yale Road.
Turn to Wildcat.
Turn on Wildcat. Okay.
And then
Turn right on Wildcat.
yep, and then where you go to Dorsey House.
Turn left at the Dorsey House. That's
And then go
136.
straight, and then you can take either way, and then.
Okay. All right. I like that. Kyle, give me directions to the mall.
The mall?
Mall.
From here?
Yep.
Okay, going School Drive.
Take School Drive. Turn right.
Then you can either go straight on Yale Road.
I'm not saying go either. I'm saying you tell me how to get there.
Turn right at the light.
Turn right at the light in Yale. So you're going south on 19.
Just keep going straight on M19.
Okay. Take M19 south.
All the way to 136. You're on 136.
So you're going to take 136. You're going to turn left.
At Broadway.
Turn left on 136 right by the BP there or the Roadhouse 19.
You're going to hang at 136.
Take that all the way till stop sign. All right. Yep. Got it. Okay. Now, if my grandma was sitting right here, God bless her soul. First of all, I give her a hug. I haven't seen her in like 10 years because, she passed away a long time ago. But if she was, and she said, you know what? I'm in town. I rarely come to Yale. I have no idea the area. I want to go to the mall. Can you give me directions to the mall? I'd say, yep. Take M19 south all the way to the expressway. Jump on the expressway. Don't go to Canada, right? I'd tell her about that stuff. But why do you think I would take her that way?
It's easier.
Easier. Not going to get lost, right? She has no idea what the Dorsey House is. She'd be looking some weird house. She doesn't know it's a restaurant. So I don't care.
It's one path.
My point here is, guys, with proofs, the idea is to get from point A to point B. How you get there makes absolutely no difference as long as you don't break any laws. As long as you abide by the rules of the law of don't speed and stop at stop signs and all that stuff, as long as you don't break any math laws, how you get from point A to point B is 100% okay. Now, and you don't get any points. You don't get extra points for doing it a faster way. Sam might be able to do a proof in 4 steps. Madeline might do it a totally different way and it takes her 6 steps. Eve might do it in 12 steps. Does anybody get more points than the other person? No. It makes absolutely no difference how fast you're getting there. It's just you have to get there. Okay? Does that make sense? Now, the tough part of this is there is no one way to do that. Like, that's what you really have to wrap your mind around. The hard part then is the same thing. There's no one way to do this. I can't give you a step-by-step, do this first, do this second, do this third. Because every single problem is different. So what we have to do, and really what proofs come down to two things. You have to be good at two things. The first main thing is your basic algebra skills. There are certain algebra skills that you absolutely have to be good at. And if we struggle with some of these skills, you are going to struggle with some of these proofs. What I mean by algebra skills are things like factoring versus foiling. Factoring and foiling. You have to know how to do that. Like, no question about it, and it's not even like I'm kind of good at it. It's got to be easier. Like, and what I mean by that is you should be able to take something like this, x squared plus 3x plus 2, turn that directly into x plus 2, x plus 1. Like, that's got to be cakewalk for you. Yes? And then also being able to go from here back up to there. Like factoring going that way, foiling going that way. Right? Simple? Factoring is a must. Another basic skill that I need from you guys. Those are lots and lots of stars. No. I need, like, this is not even like a little bit. You are going to deal with so many complex fractions over the next few weeks. You're going to get, like, you have to know how to deal with complex fractions. Absolute must. Like, cannot survive this stuff without being able to handle a complex fraction. Well, complex fraction is something like 2/3 divided by 4/5. You have to be able to simplify that. Now, how you simplify that, that is totally up to you. There's lots of ways of handling complex fractions. I personally like basically I'm going to multiply by the reciprocal method, where basically all I'm going to do is I'm doing 2/3 times 5/4. You could multiply across here. You could cross reduce. Basically, you're at 5/6 and you're done. Every single time. That's the way I like to do things, because I think it's easy. I can look at this and go, oh, all I'm doing is multiplying by the reciprocal. I'm going to multiply the top numbers, top and the bottom. That's my numerator. The inside number is my denominator. But I can do that in my head, right? Like, that's easy. Other people prefer the method of multiplying by a big fat 1. What's the common denominator? 15? I'm going to multiply by 15 over 15. What's 15 divided by 3? 5 times 2? What's 15 divided by 5? Times 4? I don't care how you get there. Fine! If Kyle likes the first method, great. Kyle, do the first method. If Eve likes the second method, then great. Eve, do the second method. So, to let you guys know, with the proof, with these next few sections, and we probably won't get to the next quest over this stuff really for about a month. Like, it's going to be about a month from now. And we're only doing 3 sections. And the reason I say it's going to take a month to do 3 sections, well, I'm kind of losing next week because now we got to start to review for the exam. We're going to lose a week because of the exams, right? So that's 2 weeks out. I mean, even if this only takes me 1 week, that's 3 weeks. That's basically almost a month already, right? So we're easily going to be about a month from now is going to be really when we're going to take this next quest. Fair enough? I don't care how you do some of these skills. You just have to be good at them, good at your way. Now, with these proofs are puzzles. They're not math problems. You can think of them exactly like a jigsaw puzzle. They have a lot in common with a jigsaw puzzle. Some people love jigsaw puzzles. They really do. There's going to be some of you. There's going to be some sick people just like me. In this room, there's probably 3 or 4 of you. They're going to come to me in about 3 weeks going, these are actually kind of fun. I like these. These are like, they're brain puzzles. I kind of enjoy doing them. And then there's going to be other of you that are just like crying at my desk going, these are the hardest things I've ever done in my life. And I don't know what's going on. I'm seeing doubles. Some people love these things and some people hate them. I'm sorry, they're puzzles. Like that's the hard part. Another basic algebra skill you need. You're going to deal a lot with fractions. You need to be able to add and subtract and multiply fractions. Now, I'm not just talking about 1/3 plus 3/4. I'm also talking about 2x over x plus 1 plus x over x minus 3. Being able to take 2 fractions like this, find the common denominator, and add these together is a must. We need to be able to handle things like this. So, let's do this. What's my common denominator? Well, I need a x plus 1. I also need a x minus 3. That is my common denominator. What was missing out of this denominator? The x minus 3. So I multiply by x minus 3 and I get 2x squared minus 6x. Yes? What's missing out of this denominator? The x plus 1. So I multiply that and I get x squared plus x. All I need to do now is add. How many x squareds do I have? 3x squareds, negative 5x's. I should be able to FOIL that out easily in my head. If you can do that, and that's an easy question, you're in good shape. Now, so you guys all know we're a little bit behind. We're not far behind. We really aren't. If this was a normal year and you were in school all year long, I can pretty much guarantee I know exactly what I'd be doing today with you. I'd be saying, all right, we're done with proofs. Tomorrow is going to be the quest, right, on this. Pretty much, yeah, we'd be doing it probably tomorrow. We're 3 sections behind where we should be. We're not far off. So now we're going to end up being a little bit more because now I got to push this back and start the next semester with it, but we're really not that far behind. We're about 3 sections behind. We're really going to only end up being 1 or 2 in the end game. So I feel pretty good that we're on pace. But because we're going to push this into the second semester, as we go through this stuff, and this goes for the virtual kids as well, if there becomes a problem or a certain type of problem that all of a sudden, hey, we're struggling, you're seeing we're adding fractions a lot and I'm just struggling to do these. If I have to sacrifice a day to go find an old Algebra 2 worksheet or something on that basic skill and we review that stuff so that when we do them with the trig stuff, it makes our life a little easier, I am more than willing to do that. So please, as we go through this, if you find a type of problem that you're struggling with, let me know, and we'll work on that one basic skill, okay? These are kind of a culminating type activity in that you're going to need a lot of little skills to be able to do these, okay? Now, a few minutes ago I said there was these come down to two things, right? No, you are going to love them or hate them. But to do them, they come down to two things. Number one, basic algebra skills. These are all the algebra skills. Add, subtract fractions, complex fractions, factoring, foiling, all that stuff. Those are all basic skills that I'm expecting that when you walked in the door, you already know how to do these. And if you don't, we got to work on those. You're going to need those skills. The second thing these come down to are substitutions. I'm going to ask you to memorize some things in here. And the reason I'm going to ask you to memorize them is not for the typical reason. Normally I ask you to memorize things like the table because 30, 45, 60, those are common angles. We see them a lot, right? We can use them to estimate things like that. That's actually not why I'm going to ask you to memorize these. We're not going to memorize them because they're common. Very few people do proofs. Like these are not, like to answer your question of when am I going to use this in my life, there's only a handful of jobs that you'll ever use this for. Actually, the only reason I still teach this is it really does teach you how to think. It's kind of a logic type thing, and it actually helps you learn how to logically think your way through any difficult problem. So that's really why I love teaching these. Now, I'm going to ask you to memorize some facts. And the reason I'm going to ask you to memorize them is so you recognize them when you see them. Some problems you're going to make a substitution on. You're going to look at the problem and go, ooh, I can start with a substitution and boom, I can move on from there. Some problems, it might be on step 2 or 3. Some problems you might make a substitution on step 5 or 6. The hard part of these, the real difficult thing on these, is you have to recognize a substitution when you see it. And if you don't have these things memorized, you're going to go right on past it and you won't recognize an easy substitution that you could make once you make it, or once you see it, okay? So the better you know them, the more it's kind of like driving. If you're completely lost, you have no idea where you are. And then all of a sudden you go, that looks familiar to me. I see something that I've memorized. That tree, I know that tree. I know that building. I've been here before. Now I know where I am, right? That's exactly the same concept of why I want you to memorize these, is because you might get lost. But then you're going to see something going, ooh, that looks familiar to me. That's a trigger. I need you to recognize that trigger, okay? In fact, everybody look at page 133 in your book. You're going to see on page 133 a pink box, right? I guess it's kind of pink. With all these identities. I'll bet you almost everybody's textbook has a Post-it note already on that page.
I have none.
If you don't have one, there's some on my desk. Feel free to put one on there. You are going to need this page. You're going to go back and forth to this particular page until you have them memorized. You need them. Now, here's the good news and here's the bad news. Eventually, these are going to be your substitutions. Eventually, this is going to be your toolbox. Okay? Right? But I got bad news for you. These aren't your tools yet. These, the way math works, the way all math works from now on, there are rules in life. you don't get to follow, you don't get to use this tool until you prove this tool. Once you prove it, it's now yours. And I can use it, and I can pull it out anytime I want. Kinda. So, our job right now is we have to prove all of these. Once we prove them, then they're ours, and then we get to use them. Now, right now, we have a very limited toolbox. And I have a reason why I call it a toolbox, and I'll tell you that in a minute. Okay. We have, in our toolbox right now, we have established some facts. I'm going to change that to a theta. We have established what sine is equal to. We have written this on the board. We have used this in the past. We know this is true. What have we established sine is equal to somewhere in this year? Come on, think about it. Yeah, think of the same thing, but put it in x, y, r terms. Y over r. Sine is y over r. What's cosine? X over r. What's tangent? Y over x. What's cosecant? R over y. What's secant? R over x. And cotangent? X over y. We've also established that x squared plus y squared equals r squared. This is our poor, pathetic little toolbox. These are very, very basic tools. We don't have much to use right now. We have basically a flathead screwdriver, we got a Phillips screwdriver, we got a hammer. We have no power tools yet in our toolbox. These are very, very basic tools. Okay? Eventually, what our job is today and tomorrow, our job is to take these basic hand tools, turn them into power tools. Okay? And yeah, I want a drill. I want a power saw, and I want some more powerful tools that I can do more things with, right? Could you, if you wanted to, build a house with very, very basic hand tools? Yes. It's going to take you forever, isn't it? Sometimes it's going to take you years. People did it for hundreds of years, but things take time, right? There are better ways to do things. The problem is we don't get to use those better tools until we learn how to use them, and we have to prove them in order to do that. So, let's take an example, the first one. Secant, or cosecant, is equal to 1 over sine. So our job right now is we are going to do a trig proof. So you might want to write this one down. Here is the very first trig proof we are going to do. When you do a trig proof, the very, very first step, they're going to look just like this. You're going to be given an equation that this is true. This is a true statement. We already know this is true. We know cosecant is the reciprocal of sine, right? Like that's a basic fact. You're going to draw a line directly underneath the equal sign. You are not allowed to cross the line. What I mean by that is this. If you were going to solve an equation like 2x minus 3 is equal to 7, what's the first thing you would do? You would basically move that 3 to the other side of the equation, right? You are not allowed to do that. Our job is very simple. Oops, I don't want to do that. Our job instead, I'm going to work on the left side however many steps it takes until it says that it's 1 over sine. I got to turn that into that. Or I can work on this side until it says what? Cosecant. And once it says, I just got to get it to match that. Or I can work a little on this side, and then I can work a little on this side, and get them to equal 2 completely different things. And as long as those 2 things are what? Equal to each other, I'm done. It's just about showing how this and this are equal to each other. Some proofs you're going to do are on the entire left side. You're just going to work on this, and it's going to turn into that. Other ones, you're going to work on this side, and you're just going to turn it into that. Other ones, you're going to turn them both into something different. Those 2 things are the same. You're good. Make sense? That's also why no 2 proofs have to be the same. Your proof and your proof don't have to be the same. Your bottom line and your bottom line don't have to be the same as each other. They just have to be the same on your paper. Does that make sense? So, let's do this particular trig proof. In our bag of tools, our very limited bag of tools, do we have something that we know cosecant is equal to, that we can make a substitution? Cosecant is equal to, we just said, we said cosecant is equal to r over y. So I can change this into r over y. There's not a whole lot I can do with that right now. That's what I would do. Now, over here, not a whole lot I can do with that 1, but I do know what sine is equal to. It's y over r. Uh-oh, I have a complex fraction. I have to be able to simplify a complex fraction. So let's simplify that complex fraction. Let's bring this up, flip it upside down into r over y. You multiply across and you get, hey, and that matches that. I'm done.
You're just dumbing down the equation.
Yes.
What's the point of the proof?
There's like no explaining though. We don't have to write words.
No words. There's no left side and right side. Guys, the geometry proofs were hard. Because geometry proofs, you did 2 steps, right? And you said angle 1 is congruent to angle 3. And what did we put on the right side? The reason. You had to write because they're vertical angles or something like that, right? This side was fairly easy, wasn't it? Like, not bad. This was the hard side. Everybody struggles with the right side. And I know exactly the reason. It's because we don't take the time to memorize all the different terms and vertical angles and, all linear pairs and all those fun words and all the different theorems. We don't have them ingrained in our memory, so we don't know what to write over here. The nice thing about trig proofs, we ain't doing that side. They're totally different than geometry proofs. Okay? Let's try another one. Let's try one. Let's try. No, I'm making one up. Cosine times tangent is equal to sine. Our job is to prove that. And I'll get to that y in a minute. So step 1, we draw our line. Sine is y over r. Great. Not a whole lot more we can do with that, right? All right. What's cosine? X over r times y over x. Multiply. What happens? What happens to my x's? They cancel out. Bam, bam. Boom. It wasn't r, and the computer got screwy. Okay? Now, I don't want you to think that these are hard. I really don't.
They're not. They just seem like when you do a math problem, you're trying to find something to get an answer. This is just like.
So here's why I love these. Here's why I love teaching these. generally speaking, I want you to think of any difficult task. Any difficult task. What does solving a difficult problem entail? Like, what are the root?
Getting out of bed.
Okay. But the way you solve any difficult task is you look at the tools that you have available to you. And you try to figure out ways that you can use those tools. And then you also have to be able to use those properly and follow some basic laws, right? Basic rules of anything. By doing this, but then you also have to be on the constant lookout for when can I use a tool? You don't know when a certain tool is going to become useful until sometimes you get in the middle of it. And you go, man, how do I do this last part? Ooh, I can use this tool in a weird way. There's a reason why I call this, and there's a reason why I call this table a toolbox. Here's why. That last proof I did, this one, it's just a version of one of your ratio identities, which is tangent is equal to, look at page 133. What does tangent equal?
Sine over cosine.
Sine over cosine. Now, we can do this proof, right? Now, mentally speaking, is this the same thing I just did? Is this the exact same equation that I just did the proof of?
Yeah.
Look at this. Cosine times tangent is equal to sine. Look at this one. Tangent is equal to sine over cosine. Is this the same equation the other one is? What's the only thing I did in my head to make up that other equation? I butterflied that, right?
Yeah.
Now, you're not allowed to butterfly this because I got to keep everything on one side. But this is the same thing as the other one. The proof is very similar. Tangent is y over x. Sine is, oops, it's y over r. And then cosine is x over r. You multiply by the reciprocal of r over x. R's cancel. And it's y over x. Now, this right here is eventually going to be, I'll call it your power saw. Okay? Let's call it a chainsaw, because a chainsaw is a little easier analogy. Okay? It's a chainsaw. You can do a lot with a chainsaw. You can cut down a tree. Huh? You can dig a hole. Cut through ice.
Break down your house.
In a pinch, it's a hammer, right? Like, if you have a tool, and the only way to use, so let's just take our basic hand tool. You have a flathead screwdriver.
You can pry stuff open.
If you only know how to use that screwdriver to tighten a regular screw, and that's the one and only use for it, it's not a very useful tool, right? You can, if you are good with that tool, you can use it in a lot of different ways. You can pry things open with it. You could use it as a hammer if you wanted to. You loose it. Like, there's lots of things you can do for it. In an absolute pinch, you might even be able to unscrew a Phillips screwdriver on a certain angle if you pry it right. It's not ideal. There might be a better tool for that job. But the more ways that I can use this, the easier your life is going to be. So I am not going to just ask you to memorize this fact. I'm not. This is one of them. You are going to use that fact 1,000 times. But I also want you to learn this fact in other forms. This is the same thing as cosine times tangent, or tangent times cosine is equal to sine. It's also the same thing as tangent divided by sine would equal 1 over cosine. It's also the same thing. Like, do you see where I'm getting these? Why? Because in a proof, I'm working on a proof. If I ever come across a tangent, I can make a substitution and turn it right into this now. That's a tool in my toolbox. If I ever run into a sine over cosine, I can turn a tangent if I want to. These are all if I want tos. If I run into a cosine times a tangent, I can make a substitution that's sine right now. In all of those different forms. So we're going to want to learn them in more than one form. Does that make sense? Yeah. All right.